Hello, welcome everybody. This is your lesson on 4.4, modeling and optimization. Optimization is the key word here. This is about finding maxes and mins using calculus. So I want to begin by just telling you that in the whole scope of these types of problems, when you're trying to find maxes and mins or the highest or least amount of something, there's this whole little broad spectrum of good calculus problems, and then there's problems that are kind of like the good calculus problems, but they're more on the ACT type of test problems. There are a few that'll overlap here, and I am going to teach you both the good problems that might be taught in a college class, and I'm also going to focus in on, of course, the AP questions, because those are the ones we're eventually going to have to get to. So you're going to get a little bit of both. So the first one is more like a good calculus problem that most people teach in, say, an Algebra 2 class, and then they reteach this same kind of idea in a calculus class. The Algebra 2 class, you'll solve this using a graphing calculator, and the Algebra 2 class you'll solve with a graphing calculator, and the calculus class you'll solve using calculus and possibly maybe no calculator, but it kind of depends on the question. So if I have 40 feet of fence to enclose a rectangular garden along the side of a barn, I want to know the maximum area you can enclose. So a lot of times with these optimizations, it helps to kind of draw a picture. So this over here is a picture of my side of my barn, and I want this little fencing here that would go on the side of the barn here. So I have 40 feet of fencing, so I know all this fencing around the outside is going to be 40. So I need to have some equations that's going to help me solve this type of problem. The 40 feet of fencing, now that's a perimeter problem because you're trying to get the distance around. But you also want to find the maximum area, so you need to kind of keep area in mind here too. So let's start by talking about area. So area is basically going to be length times width for a rectangular problem such as this. Now the tricky part in this is trying to come up with a area formula so you can then take the maximum of by taking the derivative, setting it equal to 0, and finding where you have that maximum. So the problem is I can't really do length times width or x times y because they're two separate variables. So I have to get one variable alone. So when I'm getting one variable, I haven't really used this 40, and that's a perimeter problem. So all of this outside here is going to be a total of 40. So if I think about this as being like, okay, if this is 2, and this side will also be 2, and then this side could be like an example of 5. So my fencing will be the 2 plus 2 plus 5. Well, that's not 40. So I'm going to kind of assign variables to these in place of like the numbers to try to figure this out. So if these were really 2's, and I needed a total of 40 for this side here, I would take 40 minus the 4. And that would actually be 36 feet of fencing would be over here. That gives me the 40. Well, if I don't know these sides, I call them x, and this is x too. Well, this whole side right here is going to be 40 minus the x, which is minus 2x. So I know that's getting a little sloppy, but I'll come over here to my area formula, and I'll say that my area of this entire shape is going to be length times width, so it's going to be x times 40 minus 2x. Now this is a great textbook problem, but it's not an awesome AP question because if you can't write this equation, you cannot do the rest of the problem. So you're unlocking either almost all the points for students or no points for students. So they don't like to do problems like this. They like to give you the equations. So since they give you the equations, they take this wording and make it a lot more complicated, and we'll get to that later. Now, if you're going to take the derivative, you could do this through product rule, but it's also best to distribute. So you go 40x minus 2x squared. So as I go to this next slide, you're basically seeing, okay, here's my area formula that I came up with, but I wanted to kind of talk you through it on that last slide so you don't think it's like magic and where I am coming up with it. So when you do optimizations, if you do not have a picture and it's appropriate to kind of visualize things, I would draw one. But the most important thing is to write an equation. Since you're finding maxes or mins or highest or lowest, I like to underline what the max and min is you're trying to find. In this case, it's area, so you must write an area formula. I know that 40 isn't really area, it's perimeter. You use that in your formula, but you're maximizing area, so area is the formula you need to take the derivative of. Think of it like a graph. If this is my area formula, you need that equation so that when you find the max and min and set it equal to 0 to see if it's a maximum, it's a lot easier to do that. So as you finish this problem, once you get the A, you can then go and find A prime, set it equal to 0 and solve, and in this case you get 10. Before I continue any farther, this is a video, so feel free if you want to work any of this out on your own manually. You can certainly pause the video and then continue on. So a couple things to take note here. Once you get X, that may or may not be what you're looking for. And X in this case is the width in terms of my picture, but it didn't really want the maximum width, it wanted the maximum area. To finish this problem out, you would then have to substitute your 10 back in to get your length and your width, and then that'll allow you to plug it into your area formula and to get your total area. And in this case, you know, you have units, etc. So this is just our classic problem, the barn problem. These are the steps that would help you kind of when you're trying to find maxes and mins of some sort of function. The key here is this first step. You need to write the function in terms of one variable. So the last one where I had the area equals length times width, or if I decide to go with x times y, that's no good for optimization. When we do related rates, that's okay, maybe. But in optimization, anytime you're trying to find maxes and mins, you need one variable. You need to take the first derivative, set it equal to 0, and if you have a restricted domain, don't forget to check the endpoints. So those are your steps. Here's a different question. I'm going to read now to you. What are the dimensions of a 1-liter cylindrical can, so like a motor oil can here in my picture, and I want dimensions of this can, so okay, that's what I'm going to do. That gives me the least amount of material. So let's say I work for some sort of packaging company and I need to package these motor oil or soup cans or whatever it is, and I need to find the least amount of material. So that would be, I hope you're thinking about it. When you're thinking about three-dimensional objects like that, what would that be? Is it area? Is it volume? Is it surface area? Is it perimeter? Is it circumference? Those are the things you have to think about. So what do you think this one would be? Least amount of material. Well, if you're thinking surface area, you're correct. Because if I unfolded this can and kind of laid it all out, those are the metal pieces that would make up that can, and those are like the surface area of a cylindrical object. When talking about Appendix A in the back of your book, this is where you find a lot of your geometry formulas, which may aid in you solving some of these questions, at least initially. So here's what I'm going to do. I'm going to come up with a surface area formula for this can. So this is the formula that I come up with. Now, and A being surface area. Where on earth do I get that? Well, when I'm talking about this can, I'll draw it a little bit bigger like this. I'm talking about this radius of the bottom, and this bottom is a circle. So what's the area of a circle? Pi r squared. But I have two of them for the top and the bottom, so I have 2 pi r squareds. Now the other piece, which is this piece here, if you were in class, I would show you a piece of paper that has this all unfolded. I hope you can visualize that this lateral area, which is what we call in a can like that, or a cylinder, we call this wrapped around piece the lateral area. If I unfolded this, like maybe cut it right here, and unfolded it, I have 2 ends which are circles, but this part right here would actually be a rectangle. Now in class I can show you this model if you need help thinking about it, and then you got your 2 circles here. This would be a net of this object. How do I get this amount? That would be if I folded it wrapped around a circle. So that's the circumference of a circle. Circumference is 2 pi r. And then this right here is the height. So this right here is the height of my can. So that's an h. So that's the lateral area formula. Would you have to produce this on a test? Probably not, but it's really going to be helpful later in the year if you can understand this object. What would I need to take the derivative of to solve? I'd need to take the derivative of this. Notice how I have 1 liter here. I wonder how that's going to play into it. Because if I look, I've got a radius and I've got a height, 2 variables. What can I do? Well, this conversion you won't have to do on the AP test, but let me run through it for you. The problem with this is 1 liter is a volume measurement, whereas this is an area measurement. So how do I use this 1 liter and convert? Well, the volume measurement is basically going to be, let me get an eraser here so you can see this. An eraser. I don't know. This volume measurement right here is going to be pi r squared h, and 1 liter is going to be 1,000 cubic centimeters if you use the conversion. So what I end up doing is I end up putting the 1,000 in for v, and I solve for h so that I have all r's. I could solve for r, that's another option, but then I'd have square roots and I'd have a bunch of issues, so I'm choosing to get h alone. Then this will be replaced in there, and let alone you have 1 formula. So here we go. You can kind of take a look at this. If you want to kind of pause and not look at the screen and try it on your own, feel free to do that. So this is the area formula for, surface area formula for a can by substituting in my volume for 1 liter. And you go through all this, you take the derivative after simplifying, and you set it equal to 0, and you solve. So here's my work for solving, and eventually you're going to get a really weird thing, a cube root of 500 over pi, which in decimals should be that. The only thing I don't like about this slide is there's only 2 decimals. On AP, we always use 3. Now you wanted the dimensions of the can, so of course you have to go back, plug this in for r right there, simplify, and it gives you h. Some notes: if the function you want to optimize has more than 1 variable, use substitution, and you might need to use like area and volume in the same problem, so I went over that thoroughly. If you're not sure the extreme you found is a max or a min, check. If the derivative goes from positive to negative, then you know that you will be having a maximum. That's important. And if the endpoints, if there are any restrictions, you will have to check those also, because you could have a minimum here, and this could be the maximum, and this could be a maximum, but you have to check to see if that's bigger. That's more for the AP styles. This is an interesting question, and this comes up in our book too. This is kind of making the transition from non-AP questions to AP questions. If I have this question, which is number 6 from our book, it says we want the largest rectangle, and so we want to make a rectangle here, and its base is on the x-axis and its upper 2 vertices are on this parabola. Well, this parabola goes up to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it's right here. And this parabola goes like this. And I might not be correct on my zeros, but that's irrelevant. And you want the largest rectangle that has 2 vertices on this parabola. Is this the largest one? Or would this be the largest one? I mean, I'm not really sure. So how am I going to solve this problem? Well, you want the largest rectangle, the largest area, so you write an area formula, length times width, on a coordinate plane. But the problem is, coordinate planes usually have x's and y's, so what would be the length and the width of that rectangle? Well, let's take a look at this for a second. I'm going to do this in black. This right here in a coordinate plane is an x value. This is a y value. These points are x comma y. So the x is this distance, the y is this distance. But the rectangle has this whole base as the width. So this is also an x. So my formula for the width here, I guess, is 2x. The height is y. Oh, that's not good because I still have two variables. But here's my formula for y in terms of x. So then it's really 12 minus x squared times 2x to solve this problem. And then, of course, you would distribute in. You take the derivative, set it equal to 0, and solve. If you did all this and you wanted to try it, feel free to try it. You'd get a 4 by 8 rectangle. The area is then 32 square units. This last thing that I'm going to run through here, this is a AP question. What changes here? Well, I'm going to use my laser pointer and point to a few things. So I'm going to read this. A tank contains 125 gallons of heating oil at time 0. During the 0 to 12 domain restriction, heating oil is being pumped into the tank at this rate. So this is a rate, by the way, gallons per hour. So guess what, ladies and gentlemen? This right here is your derivative. Why is it my derivative? Because it's a rate. But it doesn't say H prime. That's okay. They can label derivatives as anything they wanted. They could call it Q if they wanted to. It makes no difference. During the same time interval, heating oil is being removed. So is the level of heating oil in the tank rising or falling at 6? So this is the question, everything above this line here. Here is how they would answer this question on an AP style question. Remember, these are rates of change. This is how much oil is coming in. This is how much is going out. So if I figured out this answer using my graphing calculator, if I figured out this answer using my graphing calculator, and I subtracted them, because there's a subtraction under here, because in minus out gives you the total rate of change. This is falling at t equals 6 because you have a negative answer. Now if these weren't derivatives, as if this was not the gallons per hour, if it was gallons, I would need to take the derivative of that using a calculator. Now this may look very complicated to you just by looking at it, but eventually you're going to find that these problems are quite easy. But it's one of your first looks at them. Looking at part D, D is finding at what time from 0 to 12 is the heating oil the least. That, ladies and gentlemen, is a max and min problem. Show the analysis that leads to your conclusion. Absolute minimums occur at critical points or an endpoint, but notice how the derivative isn't equal to 0, just the rates are equal to 0 because these are the derivatives. So this would be done on a graphing calculator using the 0 feature. You get this. Then I'm not really sure what this graph looks like, but I can read this answer. I don't have the graph instituted here, but I'm guessing since the volume increases to 4.790, it probably looks like this, if this is the graph of H minus R, because then you have, I'll do this in a second, and then it probably decreases till you get to that 11 thing, and then it goes something like this. So when this function is positive, your heating oil is going up, because more is coming in than going out. So these are things that you'll have to kind of analyze when you go through a problem like that. So the minimum, if you thought about this from a perspective of if this was the gallon equation, you're increasing here. So if you start at 125 gallons, which I'm going to say 125 is right here, I'll put this in blue, right there. Then this is positive, so you're going up. This part is negative, so you're going down. This part is positive, so you're going up. So my minimums could be here or here, and then I'm going to have to compare those things. We will really focus in on that later. I just wanted to give you a glimpse of what an AP problem might look like. That's really all your questions for today. We start with more of the book problems, the ones I focused in on, and we'll get to those heating oil type questions in a little bit. But do your best if I give you an AP problem, which I'm going to give you in class to do, to see if you can figure it out and then look at the rubric and try and learn from your mistakes. Thanks for listening. I appreciate it, and good luck.